From the Library of Congress in Washington, D.C.
I'm Stephanie Marcus from the Science, Technology, and Business Division. I think it was appropriate that we had a mini derecho last night in advance of our talk on water. Today, we're going to not look into outer space, as we often do in these lectures, but we're going to look at our own planet and learn how NASA is using satellite observations to monitor water and its sustainability and security. And we're lucky today to have Dr. John Bolten from NASA Goddard. And I will have to read his title, because they always have so many titles at NASA, but for today he is the Associate Program Manager of Water Resources for the NASA Applied Sciences Program. Dr. Bolten's background is in geology with an emphasis on hydrology and remote sensing. So please help me welcome Dr. Bolten to the library.
Thank you so much, and thank you everyone for coming and spending an hour with me today. It's quite an honor to be here. So today I'm going to be telling a bit of a story about earth science and what NASA does. We have a lot of activities that are focused on observing the earth and using all these fancy tools and technology that's being developed at NASA for observing the earth. And my focus today will be on water and how we use observations from satellite numerical modeling for water security and global water sustainability. So a quick background, a lot of people say, what is NASA doing with earth science? In fact, we do quite a bit of earth science focused research and applications. And the NASA Applied Sciences program, the mission statement is to provide innovative solutions of applications of NASA satellites and numerical modeling for improving decision making. And we work with a lot of institutions around the world for improving their decision making and also integrating these solutions into their policies and their business solutions. So let's take this. Does anyone know what this is? Does this look familiar? This is a quiz. It's a current event that's in the news a lot. What this is actually a cattle farm. Okay, and you're seeing the cattle farm surrounded by agricultural fields. So why is this relevant? Why is this important? Well, we've heard about the recent E. coli outbreak. Now, in a cattle farm, if there's too much moisture in the soil, it breeds disease. And if there's too little, it leads to dust. And that dust can carry bacteria, including E. coli, and it can spread to the surrounding fields. So this is one quick example of how earth science can be applied, and it is contributing to our better understanding of our world in recent events. Here's another recent event. This is in Cape Town, South Africa. So you may have heard of Cape Town's recent struggle with water. So they actually have something they call Zero Day. This is the day that Cape Town will run out of water. And this is an unprecedented event where Cape Town, I think that the population is roughly 500,000 people. And they expect to run out of water. Initially, it was going to be in June 2018, and they've moved it forward a bit to 2019. So there's a lot of focus on Cape Town. I'll come back to this, but it's a really good example. So within water, you don't want to have too little of it. You don't want to have too much of it, right? And that's what I'll be talking about. This is another example in Ellicott City.
Ellicott City right now at a restaurant.
It's a very quick video.
That is flooding. Oh my God!
All this happened within 5 minutes.
How can you even stop it? Dude, there's a garbage can!
Pardon me, guys.
Oh, sorry. Oh, it's moving that car.
What?
It's moving. The car's going.
Oh my God. Oh my God.
Oh my God. Oh my God. cool.
Oh my god!
Oh my god, it's rising.
So that was a attention-grabbing video, but this happened a mile from my house in Ellicott City. So, in fact, an hour before this event happened, I bought a Japanese pressing of Led Zeppelin 4 right in this record store. And I was actually talking to the store owner about what hydrology is. And I said, well, hydrology it's the study of water and the forecasting of floods and droughts. I saw him the next day, gave him a hug, and he said, hydrology, I know what that is. But it's a lot of people's lives were uprooted from this event. 2 people lost their lives, and a lot of people were seriously injured. So it really brings it home. This is only a few miles away in Ellicott City. And on that note, water, roughly 90% of natural disasters are related to water. Okay, and in fact, water is now recognized as the #1 threat multiplier in the world. So why is NASA interested in water? It's because water is used for agriculture. It's used for a lot of things. Agriculture is a global enterprise. So the cost of wheat in the United States is directly relevant to the productivity of wheat in South America or Central Asia. Okay, so for that reason, we need to set our sights a little bit broader than just the United States. So on that note, we go back to, this is one of the most iconic images ever taken, right? So this is the blue marble. And it really is blue. Everything you see here that's blue or white is water, right? And if you go down through the numbers here and you think, well, let's go back to junior high school. Let's go back to the water cycle, right? It's pretty simple. Water falls from clouds, precipitates. Some of it is stored in snow, and some of it is stored in glaciers. Some of it runs down. It's stored in surface water and in reservoirs and lakes and in streams. Some of it meets groundwater. It makes its way back to the oceans and eventually evaporates up to clouds, right? Pretty simple. So our challenge here is to, as accurately as possible, characterize, understand, and predict each component of this water cycle, right? And from that, we'll have a better idea of how to assess and mitigate extreme events like these floods and drought events like that are occurring. So, we are in the blue marble, right? It's over 70% of the planet is covered by water, right? But however, only a tiny portion, about 2.5% is fresh water. So there's a very small fraction. And in fact, of that 2.5%, nearly over half of it is in glaciers. There's only a small portion that is fresh water that is available to us through surface water or groundwater. Okay, and if you look at that, okay, well, there's lots of water. There's a little bit left. Where's that water going? Most of it's used for agriculture, right? And so this is where, with the Applied Sciences program of NASA, we're looking at innovative solutions of monitoring water use. You can actually measure the amount of water that's being applied and lost through plants. So we can encourage people to move from flood irrigation to drip irrigation, more efficient uses of water. So I have a 5-year-old daughter. Her name's Lily, right? By the time she's my age, there'll be roughly 9 billion people on the planet. When I was born, there was nearly 4 billion. Okay, it's a pretty extreme trend here we're seeing. So the challenge is, how do we prepare for this increased population globally? What is their relationship with water going to be? Is there enough water to go around? I'll tell you right now, there is enough water. But if we look at the distribution of the global population density, we see some areas where there's high population, right? And if we looked at this map of water stress, so simply the ratio of water withdrawal to water availability, we see in these similar areas, the same areas we're seeing with high population, there's high water stress. So in fact, a lot of the areas that have water insecurity and food insecurity are these areas with high population and future population increases that are projected. So our challenge here is to find out how we can keep what we have, properly manage the water that is available. Now, a similar trend that we see here is This is Moore's law, okay? And it essentially says that every 2 years, the number of transistors in a circuit will double, right? So my iPhone here, if you look at this, this was another quiz. Does anyone know what this is? The ENIAC computer, right? So this is in 1946. This is considered the first, quote unquote, general purpose computer, right? So my iPhone here is 230 million times faster than the ENIAC computer. And that's just 70 years ago. So technology is advancing, population increase is also advancing. So we have all kinds of fancy tools and ways to measure different parts of the global water cycle, right? We can go out and measure the amount of rainfall, right? It's not rocket science. Okay, we can also look at snow depth. This definitely isn't rocket science. They literally just take a meter stick and measure the amount of water, amount of snow. But in fact, if you look at, let's see, San Joaquin Valley in California, most of their water is sourced by snowpack. Okay, so if they're going to prepare for the amount of water in the next season, they go out, they get a bunch of people, they go out and use these meter sticks, and they measure the amount of snowpack. Okay, and from that, they derive a snow water equivalent, the amount of water that's held in that. And from that, they can determine how much water will be available next season. Okay, you can also look at how much water is evaporating from the land surface and from plants through evapotranspiration. Okay, these are different sensors of doing this. You can also use something called a theta probe, which essentially measures the electronic resistance of the soil. So the amount of water in the soil is measured by this instrument and gives you the amount of soil moisture. You can also look at river flow. Okay, all these gauge stations, all these in situ data sets are great. And you can also look at groundwater. You go out somewhere and you dig a well and you have an idea of how much water there is. Now the problem with this is that ground stations are expensive. They're difficult to maintain. And if you look at just the distribution in the United States, this is groundwater, right? Groundwater Climate Response Network. There's not many observations here. If you look globally, this is the global telecommunication system. You can see there's a lot of areas without a yellow dot on it. And so the message here is that ground data is expensive. It's difficult to maintain. And especially when you're concerned about transboundary aquifers and crossing political boundaries, it's very difficult to share data. You know, you can have my data, but you can't have it. I can have it, but I'm not going to give it to this guy. It's a huge issue. But when you're dealing with a watershed, when you're dealing with a resource that's common to everyone, you need this common sharing of water and water data. So, going back also to 1946, this is October 26th, 1946. This is the first image ever taken of the planet Earth. And some scientists launched a Delta II rocket from the White Sands Air Force Base in California, and they were lucky enough to get this picture. And initially, they were all concerned about the clouds. They're like, "Oh, these clouds are messing up our view." But in fact, we know now that's really what we're after. So if we go back again to junior high, the electromagnetic spectrum, right? So our eyes capture the ambient light. We see colors. These colors, in fact, are only a very small fraction of the total electromagnetic spectrum, right? We're only seeing a little bit. So all this energy is coming down from the sun. Some of it's reflected through visible light. Some of it is reflected through X-rays and ultraviolet, microwaves and radio waves. So we can use these other parts of the electromagnetic spectrum to assess parts of the global water cycle. A tree looks very different in infrared or near infrared than it does in visible light. In fact, it tells us different information than the visible light. So we get beautiful pictures like this, but we're also able to look at not only is the tree green, is it yellow, but is it healthy? Is it senescing? Is it growing? How much water is it using? So we can also use different parts of the electromagnetic spectrum like microwaves, which are correlated with the amount of moisture in soil. So we're combining all these different technologies, trying to tell that story of the water landscape at that global water cycle, different components. Each different component, how can we measure and predict each part. So if you fast forward to 2018, NASA has a whole constellation of satellites that utilize different components of the electromagnetic spectrum for focusing and monitoring different components of the water cycle. And we're also collaborating with the International Space Station. We have instruments there that stay on for about 1 to 3 years. And what's unique about the ISS is it has a slightly unique orbit, so it captures things that aren't captured by other satellites. So the whole idea is, as frequently as possible and as accurately as possible, monitor different parts of that water cycle. So I'm going to show a few examples of what we're seeing from space. This is one of NASA's recently launched satellites called the Global Precipitation Measurement Mission, GPM. So instead of just having a few gauges all over, we can now have every 30 minutes on the planet, we have an estimate of precipitation, right? Not just over land, but over sea as well. And this is extremely powerful if you're interested in, if your business is hydrology, okay, and figuring out where the water is and where it isn't. Another satellite that is widely used is MODIS. It's the Moderate Resolution Imaging Spectroradiometer. And what's really neat about this is you see this sort of pulsing, this breathing of the planet. And you see a growing and senescing of vegetation, right? And this is sped up, obviously. But through MODIS, we get frequent observations of vegetation health. And this is one of the most widely used satellites that NASA has. A couple missions that are up and coming, about to be launched, are exciting. One of them is called ISAT. And what this is using LiDAR, or laser altimetry. And think about this: from space, from several hundred kilometers up, you can detect the height of water or a glacier within the accuracy of centimeters. Okay, this is a highly anticipated mission, as well as the Surface Water Ocean Topography, or SWOT mission. This uses a slightly different technology. It's a synthetic aperture radar interferometric system. I was nervous about saying that, but I did it. So, but this also, the idea here is to measure the topography of the ocean surface, and also the rivers and reservoirs. So I just find it pretty amazing to think that from hundreds of kilometers up, you're able to tell the height of a reservoir, a lake, or even a river within the accuracy of centimeters. It's pretty wild. One of my favorite missions to talk about is GRACE. It stands for the Gravity Recovery and Climate Experiment. And there's a follow-on mission to be launched here in about the next month, GRACE 2, or GRACE follow-on. So, but what makes GRACE unique, it's not a satellite looking down at the Earth. In fact, it's two satellites flying in tandem that are looking at each other. They're not looking down. So they're looking at each other, right? And they're looking at each other, and they're measuring this horizontal distance within the accuracy of one red blood cell, if you can believe that, right? So if there's a mountain or a large landmass here, that first satellite will be pulled forward just slightly, and this horizontal distance will change. Okay, and they keep on doing that. They go around the planet, go around and go around. And what they're doing is they're mapping the gravitational pull of the Earth, of the different landmasses. And a change from 1 month to the next is a gravitational anomaly. Now, mountains really don't move that quickly. So if you see a large anomaly, you can infer a movement of water, because water has mass. And so, in fact, what you're seeing here, these different colors, are the terrestrial water storage anomalies. And this is really a game changer for hydrology, because we're always trying to solve the water budget for our residual is always groundwater. What's the delta storage? What's the change in storage? Well, now we have a direct observation of that change in storage. And it's a truly novel satellite mission launched by NASA. Now, this is really cool. first of all, I think that Bob Ross would probably be super jealous of the happy clouds here, because what you see, all this is two satellite observations laid over each other. So you have a satellite-based soil moisture observation shown here in blue and orange. These are soil moisture anomalies. And the yellow and red are GPM precipitation. Right? It kind of makes sense. Where it rains, the soil gets wet, right? But it's really useful for helping convey this concept of precipitation memory. Where is it raining and where is it not? Where is the water holding water? Or where is the soil holding water? Or where is it not? And it's become a pretty cool educational tool. But it also is really useful for just showing the utility of combining multiple data sets from satellite and helping tell this story of the global water cycle more completely. So back to the water cycle. All right, so we have all these different observations. We're sensing precipitation. We can detect rivers and reservoirs and all this stuff. Okay, but what do you do with it? Well, where the rubber meets the road really is through numerical modeling and land surface modeling. And all that is an estimation of reality, right? It's based on physical equations that are hopefully physically consistent. You're trying to mimic what you see in nature. You're trying to mimic how, if a certain temperature and pressure in this cloud, when will it precipitate water, right? It kind of makes sense. A lot of these equations have been derived in laboratories, and then they're applied to real-world applications like we see here. So we have all kinds of different equations and numerical models that we integrate these observations of satellite. We take these observations of in situ observations and gauge data, and we just try to tell that story more completely in a way that is physically consistent and makes sense and that we can use. And when you understand what's happening now, you have a better idea what's going to happen tomorrow. And that's what it all boils down to. So back to the blue marble. Where are we? So it's something that I think most people are familiar with is the drought that occurred in California a couple years ago. So if you just look at the terrestrial water storage changes in California from the GRACE satellite, and you can see here what we're seeing, there's a little red dot that goes, and you can see this trend, significant decrease in terrestrial water storage. And it repeats. And this made a lot of headlines in the news because, for one, it's very easy to see, okay, red is bad, blue is good. California, it's going down. But what it did is help tell part of that water landscape story for California. Now, if we go back to Cape Town, right? So let's say, Cape Town says they're going to run out of water. They're experiencing a drought. Okay, well, what does that mean? How can water managers there prepare? What are they going to do? Is it really a drought, and how extensive will it be, and how long will it last? What happens? So the first thing they do is you look at the climatology, which is essentially just a long-term record of weather. And every area has its unique climatology. So this is what's happened in the past. What is it going to look like today or tomorrow or next year? So we use numerical modeling to look at seasonal forecasts. Okay, and you say, well, what may it look like in May to July of 2018, all the way up to September, October 2018? It's very similar. In fact, it's the same thing you see when you turn on the weather channel, right? Those are short-term forecasts. Well, there's long-term forecasts as well, but they're all based on the same thing. You need accurate observations to initialize those models, and you're providing estimates, in this case, of future climatology or future forecasts of the weather. So what does soil moisture look like in Cape Town, and how is that related to the drought? Well, the whole idea is having a long-term record, have a historical perspective of all of these variables of the global water cycle. So we see here, if we look at an anomaly of soil moisture, we can look at this year's soil moisture compared to last year's. It's very straightforward, very simple for that point. But then if you isolate different areas of in this case of Southern Africa that are used for agriculture, well, soil moisture is a leading indicator of agriculture, of drought, right? So we say that the soil moisture anomaly we have now is a leading indicator of vegetation next month or next week. So we use this as a way of forecasting future agricultural drought. In fact, the definition of agricultural drought is a deficit of soil moisture. So soil moisture is dear to my heart. I've been studying it for years, and it's turned out to be one of the most important variables in hydrology, because it's a boundary condition between the land surface and the atmosphere. Just like your body, when you get hot, your body sweats, right? And that evaporative cooling cools your body down. The same thing happens on the land surface. So the amount of moisture in just the top 1 to 5 centimeters of soil has a direct influence on that local weather and global climate. So, and it's really used for initializing climate models. So this image shows the African Drought Monitor. This is by the Princeton Climate Analytics Group from Princeton. And you see this, and they've taken these data, and they've derived a soil moisture drought index. And you just see from one change from this is April 22nd, 2018 to April 29th, 2018. And the whole idea is putting this in a story that makes sense, that is relevant to the previous days and future forecasts for that area. So I'm focusing on Cape Town for a couple reasons. One is because it's in the news. And two is that we're collaborating with several other agencies to try to assess and help the city of Cape Town and the country of South Africa for assessing their current drought conditions. And so we were working with the Department of State, and we had a bunch of people come in and say, well, what's happening in that what's happening right now? Well, if we look at the reservoirs, thankfully we have a relatively long-term record of reservoir storage. So these are the 6 main reservoirs that feed Cape Town. And you don't need to be a hydrologist, you don't need to be someone from NASA to look at this graph and say, I see a trend. These are decreasing, okay? Well, it's not just that, it's about how much water is being used, right? And how much you expect to have. You can also look at stream flow within the area. But what if there aren't gauges there? What if there's a lack of it's a poorly dense network of stream gauge data? Well, we can model that stream flow. And so that's what we're showing here. We have several different models, and we're looking at our modeled stream flow compared to our observed stream flow. What does groundwater look like? So we're using gray. So this is in the Orange River Basin in that same area. So you have a historical record of terrestrial water storage and evapotranspiration as well. So my point here is we're going through all the different components of that water cycle that I showed earlier and saying, well, you know what, from MODIS and numerical modeling and other things, we're able to look at, in this case, at evapotranspiration. And what does the spatial distribution of evapotranspiration look like in that area? You boil this all down, and what you want to get is a metric of water stress. We're not interested in just pretty pictures. We want to know, what's it look like? What's really happening? Okay. But where it really matters, okay, you take all this data and all this fancy pictures and stuff, and this is a busy slide on purpose, okay? What this is moving from data to decision making. Okay, this is a dashboard that's been provided to the city of Cape Town. And they have a % of dam storage that's currently available, the future yield changes, and they have a lot of historical perspective put in and tied to the current conditions of Cape Town, all relating to reservoir storage, current drought conditions, current precipitation, future forecasts of that water. And that is what it's all about. Now, if we go back to flooding, Delicate City was a pretty scary video, right? Well, we've been partnering with the Applied Sciences program of NASA has been partnering with Thailand and groups in the Lower Mekong River Basin. So we've been working with the Mekong River Commission and the Asian Disaster Preparedness Center, working with them because in the Lower Mekong River Basin, there's nearly 60 million people who live there, and their livelihoods depend on the Mekong River. That's their main protein source. But it's also one of the most heavily dammed areas in the world. And it's affecting a lot of things. And it's also an area that is extremely prone to massive flooding. So we've developed a system for assessing near real-time mapping of flooded areas, right? Combined with socioeconomic data. Okay, so you can tell us, say, hey, it flooded there yesterday. I can see because the MODIS data looks a little bit different. This vegetation is covered. Okay, that's great. But in addition to just where your boots are going to get wet, what's really useful is saying, well, this is the percent of the population that's affected. These are the acres of rice that have been inundated. These are the number of schools and hospitals that have been flooded by the event that happened 12 hours ago. That's moving from data to decision making. So what we've come up with, and this is a paper that was just published 2 weeks ago, we've tied this with a damage assessment system, where they've tied this, they have essentially levels of flooding are tied to a monetary value of damage. And so we can tie this all in together. We can come up with a rapid assessment of dollars of damage. And from that, you can allocate resources. You can focus areas of interest for mitigating flood damage and flood risks. So here we're working with our friends here from the Asian Disaster Preparedness Center. We're all huddling around. This image was not staged at all, but we're huddling around and we're building a system. And the idea is that we're taking this technology that's constantly developing, and we're working with it to develop something novel. And this is a little video of something that we're developing for the Asian Disaster Preparedness Center, so that they can take this data and then they can use it to tease out information and improve management of, in this case, the flood management mitigation program. This was sent to me this morning at 6 a.m. from Bangkok. So this is, for me, it's really exciting because we're I'm taking all the great innovative data and cool things and working towards capacity building, working towards understanding our world better and managing that water in a more efficient way. So we have lots of satellites, we have lots of data. I had some crazy stats about how fast computers are now. Well, this graph is also following that same population trend graph, and but what you see, this is actually, it shows the archive volume just from NASA alone of data stored. And on your y-axis here, this is petabytes of data. So we are inundated with data. There's tons and tons and tons of data. And this is only going to increase, right? And for that reason, we're embracing high-performance computing and cloud computing, especially if you're interested in providing solutions for areas of the world that are water insecure and food insecure. A lot of times those are the areas of the world that also lack high computing capabilities. They don't have giant Linux servers, readily available, or they don't have the time or technology for storing all this data. So by moving towards cloud computing, we can develop solutions here that is widely usable by people and it's easily accessible. So this is a new trend on the horizon here. So I've given you a very quick overview of some water resources applications things, but I encourage everyone to check out the NASA Applied Sciences program. It's a wonderful program. We have many, many, many exciting things that I didn't get a chance to discuss today. So I encourage you to go to the website here. We have examples of different projects and an entire list of all our partners and end users that we are working with to develop these innovative solutions. And my last slide, this is my daughter. And this is water. She's in the shower. So I just want to leave you with, our task here is to really embrace technology, understand science. We see that just within the last 70 years, we've had a dramatic increase in our computing capability. We've had a dramatic increase in the number of satellites or ways to view the planet Earth from space. And now we have the ability to integrate all these data and all these new technologies and provide them to people for improved capacity building and improved understanding of our world. And I'm always thinking, what kind of world am I going to leave for my daughter? What is her relationship with water going to be? Will it be better or worse? Well, she's smiling right now, so I'm happy. Thank you so much.
Thank you. You said you'd like to talk and you've got more time, but hopefully we'll have a lot of questions and you can always fill them out with more information.
Sure.
We'd like you to repeat the questions so that everyone can hear it, and go right ahead.
Yes, sir.
Are there any plans to deploy any of this water technology towards other planets in our search for water in Mars and other places?
So yeah, the question is there do we apply some of these technologies for for other planets? Well, a lot of these technologies have developed in parallel with. It's the same technology. In fact, the GRACE satellite that I showed, that actually came from I believe it was a lunar mission. And so the answer is yes. I'm sure you're familiar with the Mars and the Mars rover. I actually share a coffee pot with these guys, and they're on Martian time because they have to babysit the rover. But that's using the similar technology. So the answer is yes, but it's more difficult to get some of these in space. The soil moisture mission that I showed, the soil moisture active passive mission, you really need a passive instrument, a passive aperture or antenna in space. And it's really difficult to get something that's, in this case, in microwave in the L-band frequency. So you need the wavelength is pretty long, about 21 centimeters. So to get something in space that can capture that relatively weak signal, they had to develop this very novel dish system that would fold up into a rocket. And when it launched into space, and then it folded out into this beautiful array of antenna. And that was the first of its kind. And that was just launched in 2015. And the future looks bright. Yeah. Yes?
You had a slide that talked about how much of our pure fresh water is in glaciers. I'm just curious, there's been a lot of declining glaciers.
Mm-hmm.
So is that affecting our ability to have fresh water?
Yes. So the question is the declining in glaciers affecting our fresh water? So this is an entire area of research that is widely focused on right now. I mentioned the ISAT mission, and one of its purposes is measuring glaciers, the change in glaciers, and the change in ice storage of water. And I also mentioned Cape Town, and it's really not a joke anymore, but they've actually estimated it would cost $130 million to tow a glacier to the city of Cape Town to provide fresh water. And this is seriously being considered right now. But as far as climate change and understanding global climate and relating that to glaciers and what we're seeing is the decline in glaciers, it's a significant part of that equation of the global water cycle. So the answer is yes. And I could talk about this all afternoon, but it has a major impact on ocean circulation and resulting climate. So there's all these future. I showed a few of the climate forecasts, but there's a big school of these forecast systems that incorporate global ocean circulation and also incorporate future climate scenarios where they have a scenario analysis of withdrawing glaciers and melting of that water and the additional fresh water into that system and what will happen. Yes?
So regarding sustainability going forward, are you making forecasts about long-range forecasts about future sustainability and what the policy options might be for addressing those?
Good question. The question is looking at future sustainability and future implications of water sustainability. And the answer is yes. And what I showed here was really just one part of that equation, right? I showed the Earth observations. Another part is management of water, political will, which is a huge component, and management of those resources. And that's where it takes more than just someone looking at satellite observations or numerical modeling saying, okay, this is what might happen, but also a sharing of those resources. If I can encourage a group of people to move away from flood-based irrigation towards drip irrigation, or if I can encourage them to say, well, look, this is the impact that building 13 dams on this river in the next 10 years will happen on the fisheries will have on the fisheries industry, will have on the local agriculture industry. And that's where we take these scenarios we have, and hopefully we can work with governments and work with and hopefully inform these future decisions. So the answer is yes. And not everything can be solved by a satellite. A lot of it comes down to working closely with people in that country, because every disaster and every water need is unique, and every solution must be unique to meet that. And that's what's really cool. It's kind of job security for us in the Applied Sciences program, because there's so much need for understanding water. If you have these scary statistics and say, yes, the number one threat multiplier in the world, there are well, I'm not going to go into it, but there's a lot of examples of where water has led to a lack of water, or too much water has led to uprisings and not good things. Thanks for the question. Yes. In the back.
All right. This is a related question, but maybe a little bit more on the technology. And I apologize, I came in a little late. Possibly you touched on this at the beginning, just let me know. But it seems to me that when you're dealing with satellites and sensing of what's happening with water, you're also wrestling with really three forces that are hard to wrestle with and take a lot of smarts. It seems to me, and probably data that isn't available from satellites. One is just natural variability.
Mm-hmm.
Showing your kind of cycles and what's going on. Second, which complicates it, which we've talked about a fair amount, is climate change. So there's a long wiggle as well as a short wiggle going on. It's maybe not a wiggle, it's a long-term trend. But the third is also the demand component, what's happening with human demand for water,
Right.
which is much harder to get at. And I'm just curious as to how you wrestle with that and integrate that into, for example, a consideration of drought. Drought is in some ways a natural effect, but it also is affected by the demands that farmers are making on soil, for example, on irrigation sources, and population generally. For example, in Cape Town during this whole crisis, Cape Town's population has continued to grow by tens of thousands
Mm-hmm.
a month. So more and more people are coming in to demand water. A particular research question I've been trying to wrestle with is Lake Chad is disappearing.
Mm-hmm.
Something similar to the RLC. Some people say that there's climate change at work, and other people point out that the number of farmers withdrawing water from Lake Chad has been increasing dramatically. Population growth is extremely rapid in that area. And I'm just wondering how do you integrate some of your satellite measurements with demographic analyses and socioeconomic analyses that actually show the impact of increasing demand? And how much of the picture is that?
Excellent question. If I can boil it down, it's essentially how do you capture demand for water, and how do you capture local management, local demand into these strategies? And well, using Lake Chad as an example, I was planning to go over there and dig a number of wells with the local universities, but Boko Haram came in and I wasn't allowed to go. But you really don't. It's difficult to learn more than you can by working with locals, because they have their local practices, they have their local demands, right? In regard to the climate change question and all this, it all boils down to understanding and capturing the processes, in this case, of the water cycle and the energy cycle and the carbon cycle, because they're all interrelated, right? And moving from the very different thing between beliefs and knowledge. Okay, well, I know something because I observed it. I know something because I've observed it, I predicted it, and I've seen it again. And if you don't believe in something, that's something entirely different. So it all comes down to repeating these observations, having a historical long-term record of observations, In this case, as you mentioned, there's different scenarios or different causes of and components of climate change and how it will be realized. But something that we are observing is that it'll be realized mostly in the water cycle. Okay, and that's being seen, has been seen for years and years. So as far as integrating these local management practices, that is kind of in this field of applied sciences and water management, it's one of the most difficult things to work and take in the local approaches to, in this case, agriculture, right? If you're looking at Lake Chad, or if you're looking at Cape Town, and to find a solution that if I come in and say, oh, you guys need to change everything you're doing, we know everything, that's not going to work. It definitely will not work. But if you try to embrace a bit of what they're doing and try to integrate in a meaningful way, so we can compare apples to apples, saying, okay, well, the soil moisture that you're seeing here is directly related to the amount of crop yield you'll have in 2 months or 3 months. And we can use this as a way of forecasting that future yield. That's very powerful, and it's very powerful for helping, in this case, a country or region change their management practices in regard to agricultural productivity. Yes, sir. Oh, I'm sorry. Yes, sorry, she was up first.
Yeah, so you showed a really nice slide of water stress, and I was surprised by some of the areas. Are there regions or countries that are approaching a similar circumstance that exists in Cape Town?
So the answer is, are there other areas that are experiencing the same conditions as Cape Town? Yes, absolutely. In the United States alone, let's take the United States. 2017, there was a widespread drought in northern United States. 2012, there was a widespread drought in the United States that led to over a $50 billion loss in revenue just from agriculture alone. There are a number of examples of increased water stress and increased demand on that water. If we go back to the global population increase and what that really means, if you look at, a lot of the area of increase was in India and Asia, right? That increase in population and also the increase in technologies leading to an increase in middle class. Middle class are consumers. We consume more, and we eat better food. We eat more meat. That meat requires more water to produce. All these things are taken into that calculation of water demand. It's not just how much water I use to brush my teeth in the morning or how much I drink every day. What also needs to be considered is the amount of food that I consume, the amount of energy or water that's being used for hydro production, and water is used in other ways of industry and agriculture, as we saw, is the number one use of water. Yes, sir.
Could you say something about desalination?
Desalination. So the question is desalination. So desalination is the removing of salt from water, right? And even though 70% of the planet is covered by water, most of it's salt water. Desalination, a few issues with desalination. I think it's a great area of research, but it is extremely inefficient. It takes a lot of energy to remove salt from water. If you look at the city of Dubai, almost all of their water is sourced by desalination. So I heard a stat, don't quote me on it, even though I'm on video and at the Library of Congress, but I heard that without desalination, they would run out of water within roughly a week's time. But I did see a presentation just last week about the whole slew of new desalination approaches, and something that they're moving towards is sort of a sustainability approach of desalination based on solar panels and other ways where you can overcome that relatively expensive part of desalination. But it seems like it would be hit the nail right on the head as far as a way for finding fresh water. I think you had one.
Well, I was just wondering learning about other space agencies or countries in the developed world and coordinating with them? They must have their own fleet of satellites who do the same thing, or they just feed off your?
No. So the question is about other agencies and other countries that we're working with. So NASA partners with all of them, and we're developing a sensor called NISAR that's developed by the Indian Space Agency. We're working with a lot of the European Space Agency satellites. There's Sentinel satellites that complement a lot of the observations that I showed today. We're working with JAXA of the Japanese Space Agency, all of them. And this is what's really exciting, because you're partnering with all these different countries and different agencies, and they have their own approaches and unique solutions to driving a lot of these. And some of these we partner with them in the development of these satellites. And it's a really good excuse for running around the world and working with incredibly smart people. Yes, ma'am?
You've been talking about government agencies and in many different countries. What about the international corporations that draw water from the earth and sell it? I mean, I drink bottled waters, but so I'm one of the sinners. But do they use the information that you are developing, these international corporations, which are sort of countries of their own? I mean, they span the globe in many ways.
Sure.
They use your information for your work?
Yes, so I think the question is international corporations and how they apply the data that I showed today. And the answer is yes. Well, international organizations, if you mean for a for-profit institution, if you take Coca-Cola, for example, most of their business is based on water, right? And we are partnering with Coca-Cola on a number of ways. I forgot to mention, I should have said this at the beginning, but every single piece of data that I showed today is in the public domain. Everything NASA does is free for use. And that's what makes us a bit different. And we encourage organizations to embrace this. If you understand, in this case, where the water isn't and where the water is, hopefully that will be managed in a way that's for the greater good. But there are, I have no idea of the number of users of NASA data or how that's being applied. But I do know that we work with organizations such as the United Nations. We have a couple projects that I didn't show that are actually endorsed by the G20 initiative that are focused on providing global pictures of, in this case, it's the GeoGlam project, which is focused on water and its relationship to global agricultural yield. We're partnering with USGS and other agencies for a project called FuseNet, which is focused on the food insecure areas of the world. Okay, but we're also enabling people like these international agencies to have their own solutions for water management, and that's something that NASA is proud of. This open data policy.
What specifically is Coca-Cola doing?
Well, they find water and use water to develop their product. Yes. Oh, sorry. So so Coca-Cola is interested in looking at the forecasting of water. I mean, exactly what we're looking at here. So they have bottling plants. They have areas where they're collecting water and using water. So how much water is available? How much water will be available tomorrow or next year?
So you're directly working with them to figure that out.
They are one of our end users for the Applied Sciences program. Yes. Yes, ma'am.
Drone use for the agriculture monitoring is very active now, and any collaboration, the fine-tuning information with satellite work and drone.
That's a good question. So the question is about drones or unmanned aerial vehicles. So this is a really exciting field, and the answer is yes. So NASA, in fact, has a lot of drone technology as well. Because as the technology advances, the sensors get smaller, things get lighter, you have more storage, and you can throw something on a tiny little helicopter or plane. And we also have something I forgot to mention as well, called CubeSats, which is a cool word for just small satellite. So you have a satellite about as big as this water pitcher. that you can throw in space, and for a fraction of the price of a traditional satellite mission. And NASA is famous for having some wonderful, amazing, very impressive, and long-lasting satellite missions. But I think something on the horizon here is the UAVs and the CubeSat technology, because you can throw a swarm of CubeSats in space for a fraction of price, and this whole life cycle of concept to launch, which is relatively long when you think of a long satellite or a large satellite mission, is a little bit smaller when you have CubeSats and UAVs. But I've seen a lot of UAVs used particularly in agricultural applications for precision ag. You can throw a thermal sensor on a drone and other sensors now, and it's really neat. And what's just in the past 10 or 15 years, because of the speed of computing and how cheap data storage is, you're able to do that. So it's a really exciting innovation. Yes, sir.
So if we've been collecting data of this type long enough to not just see variations, but make real trend predictions.
Have we been able to?
Right, because I don't know how long this kind of detailed data has been actually collected.
Okay, so I guess the question is, how long have we been collecting data for these, to put it in a historical perspective? So,
Or to be able to identify honest trends as opposed to just variations that you're showing.
right, and that's, I can give you sort of a weird answer, but it's each one of these. Let's say if we take soil moisture, so I deal with soil moisture a lot, and if I have 1 or 2 years of soil moisture, I'm not really going to be able to derive a reliable anomaly from that. Okay, but if I have 10 years, maybe I will. The idea with soil moisture related to agriculture is you want to see several growing seasons, and you want to capture extremes in those growing seasons and extremes in that hydrology. If you're looking at flooding, you want to see a year that was at an extreme. You want to see a year that was also at a very low extreme, so you can capture those. And when you do that, you have a better sense. The lifespan of NASA satellite missions are all unique, but I think to be conservative, they throw them up there to be roughly 3 to 5 years. But we've had many satellites that have lasted longer than 10. And this is, I'm not on a soapbox, but if I was, the importance of having concurrent observations and keeping this consistent record. That's why in the next few weeks we're going to have a GRACE follow-on mission, because the GRACE satellite or the GRACE mission just died. It's still floating around there, but it stopped sending data. But if we miss a few months of data, it's really a huge loss if you're trying to paint this historical perspective. If you're looking at the state of California, okay, well, I know what happened from 2010 to 2015, but if there's a couple year gap there, that's going to be a really big loss for that data set alone. And that's something that I'm always trying to remind people of, this importance of, you need to plan now for the next 10 years, and we need to start planning for throwing a mission up that can contribute and capture the same observations, so that we have that will improve the utility of that data record. Thanks for the question.
Any others before we end?
Sure.
So are you working with an interagency working group that takes your data and tries to develop applications?
Yes. The question is, are we working with an interagency working group? In fact, we work with USAID, we work with the World Bank, we work with the United Nations. There's a separate subgroup of the Department of State called the Interagency Water Working Group that, in fact, I showed 1 or 2 slides from those meetings. And the answer is a big yes. Yes, sir.
I don't want to make you uncomfortable, but the political trends aren't so good for your record consistency, are they? Isn't the NASA budget that the Trump administration is promoting and that Congress has in fact approved, pushing more toward extraterrestrial, going to Mars, doing things on the moon, but sliding the budget for Earth observation?
Right. So the question is in regard to current administration and the focus on, let's see, yeah, we're not supposed to talk. But the answer is current administration has been we've fared very well with the NASA Earth Science budget, and we have a lot of exciting missions on the horizon. So, thank you so much for coming, and
you all.
I'll be around, and I love to talk about it. So.
This has been a presentation of the Library of Congress. Visit us at loc.gov.